Hello and welcome to another video on Caesar algebras from a novice perspective. Today we're going to talk about ideals and quotients of a Caesar algebra and describe some fundamental results that we will need later on. And basically, how do homomorphisms of Caesar algebras actually work? And previously we talked a lot about the continuous functional calculus for normal elements and how it led to a rich theory for self-adjoint elements. And for instance, if A here is a self-adjoint element, then the spectrum of A is contained in the set of real numbers, and the norm of A is just the spectral radius of A. So this is very convenient for self-adjoint elements. In particular, if the self-adjoint elements were positive, meaning that their spectrum was contained in the set of non-negative real numbers, then you can do a lot more. So then you could talk about how these positive elements correspond very well to the notion of positive numbers in the complex plane. And we used all this to prove that every Caesar algebra has an approximate identity. That is, it's a net of positive elements that more and more resemble an identity in the Caesar algebra, even if the Caesar algebra is non-unital. And more explicitly, this approximate unit is given by this explicit expression here. So this E sub lambda here is normally called the canonical approximate identity or approximate unit. I will use those words interchangeably going forward. And we begin by talking about ideals. So in the context of Caesar algebras, if we say nothing else, then we tend to mean norm-closed and two-sided ideals. So if I don't want that, then I have to say it explicitly. And now it's important to note that if we didn't have this norm-closedness of the ideals, then we couldn't really do a lot of what we are going to do in this lecture at all. And as an example, or maybe the most important example, is that of the kernel of a non-zero homomorphism. And one can not, without much effort really, deduce that these ideals that are kernels of non-zero homomorphisms are both two-sided and norm-closed in the context of Caesar algebras. And this has to do with the fact that homomorphisms of Caesar algebras are actually continuous, as we shall see. Now let us go to the first sort of minor results of this video. And that is that if we have A here to be a Caesar algebra, then every ideal of A is self-adjoint. Meaning that if I here is an ideal, then it's equal to I star. And I star is simply like if J here lies in the ideal I, then J star lies in I star. It's really that simple. And these are the same. And how do we prove this kind of theorem or this kind of lemma? Well, we actually have to use approximate units immediately. So if I here is any ideal of A, then we can set B here to be equal to the intersection of I and this I star. And then it's not very difficult to check that B is actually a Caesar subalgebra of A. It inherits the norm and all that, and because of the fact that these ideals are norm-closed, we don't run into any issues when it comes to the algebra being a Banach algebra or anything like that. And in particular, we note that B contains this particular set, that is every element of the ideal multiplied by the conjugate of another element in the ideal. And since B is actually a Caesar algebra, it does also contain an approximate identity, which we denote by this E sub lambda, as usual. And now we can use all this that we have established to do the following calculation for any element I inside of the ideal. So the limit of I star minus I star times this approximate identity squared. Let's see here. there shouldn't be a 2 here. Yeah, this should not be here. So this limit here of this norm squared is equal to this limit of this norm simply here. And this is just the C-star property that we have, that the norm of A squared is equal to the norm of A star times A. So that is, here we have the norm of our element squared, and here we have the norm of the same element, or we have the norm of the element times its star, basically. So when we do all these calculations, we see that here I times I star, it lies here, and I times I star times E sub lambda lies in B, and therefore this whole expression lies in B. And this expression is the same as, and of course, let me just do that. And these two expressions are, of course, the same expression. So by the definition of an approximate identity in B, this has to be 0. And what can we really say from this? Well, since E sub lambda here lies in the ideal I, then so must I star times E sub lambda by the definition of ideals. And hence, since the ideal is norm closed, it means that I star here must also lie in I because its distance from the ideal is 0. And therefore, we have that this ideal is self-adjoint, as we stated. And once we have this lemma, we can state the first kind of important theorem for us. And it's also another reason why we only consider norm-closed ideals. And that is that if I is an ideal in a C-star algebra, then we can take the quotient A divided by I and quotient I out this ideal, and we still have a C-star algebra afterwards when we endow this quotient with the following quotient norm. And now, if the ideal is not norm-closed, this norm would not be a norm, it would only be a semi-norm. Because you could find elements in the quotient whose norm would be 0. So let's look at how we actually prove this theorem. And the first thing we do is we establish some notation. So we write a dot over A here to denote the coset A plus I here, which is of course in the quotient. And note from the previous lemma that this ideal is actually a C-star algebra because it was self-adjoint, so this set B, which was the intersection of I and I star, that was the C-star algebra, but that is simply I here. So it's a C-star algebra, and hence it contains an approximate identity. Moreover, since this ideal is self-adjoint, we have that the norm of A dot star is actually equal to the norm of A dot. And this, you can think of it as basically if you have A here and you have A dot here, then the ideal is somewhere here. Then due to the fact that the ideal is self-adjoint, every element that is at a certain distance from this element must correspond to an element, say here, which is at an equal distance from the star. So there is nothing more to that. And now we begin by proving the following, that the norm of A dot here, which is in the quotient, is the limit of A minus A times this approximate unit for the ideal. And let's see how this works. So note that since A times this approximate unit E lambda is inside of the ideal for any element in this approximate unit, then of course by definition that we set up in the beginning, the norm of A minus A times E sub lambda must be greater than or equal to the norm of A dot. And this is sort of trivial by definition. Now conversely, for every epsilon greater than 0, there must be an element I inside of the ideal such that A minus I has norm less than the norm of A dot plus this epsilon. And now we simply do some calculations. So from the triangle inequality, we get the following results here. So when we take the limit here of a minus a times e sub lambda, we get by the triangle inequality the following. And let me just explain what happens here. So if you take this expression, or what's inside of these norm brackets, and what's inside of these norm brackets, you get back precisely this thing here. So that is basically something you can check if things don't work out. Just expand this expression here and add this expression here, and you should get back this expression here. And then by the triangle inequality, you get this result. Simply that the norm of a sum is less than or equal to the sum of norms. And now we can actually take limits here and see what happens. So first off, we note that this limit must be less than or equal to this norm here. And why is that? Well, it has to do with the submultiplicative property of the norm. So notice here that the norm of this product is less than or equal to the norm of this factor times the norm of this factor here. And thus, we have to see, okay, what is the norm of this factor here? Well, it is less than or equal to 1 because e sub lambda is a positive element. And that is the trick. So no matter which lambda we have here, e sub lambda is always a positive element that is less than or equal to 1. And therefore we get this part. But now you may ask, okay, sure, but what about this term? Where does it go? Well, here we actually use the fact that e sub lambda is an approximate unit for our ideal, and the fact that I lies in the ideal. And that simply means that by definition, this term tends to 0. So we get that this is less than or equal to the norm of a minus I, but the norm of a minus I, as we have it here, was less than or equal to the norm of a dot plus epsilon. And now we just basically let epsilon tend to 0 to see that this claim has to be true. But this was not really what we wanted to prove. We wanted to prove that the quotient algebra is actually C-star algebra with this norm. And proving that this quotient norm is submultiplicative, that it satisfies this property, is not something that I'm going to go over. It's something that you can either look up or do as an exercise for yourself. So left is then to check that the C-star property holds. And this we can do in the following way. So the norm of A star A, and I will just say A star A or A, even if there is a dot above it, I'll just say A star A like this. That is equal to, by definition, as we just saw, the limit of this expression here. And now we use the submultiplicative property again of the Banach algebras. So that means that if we multiply by this element, then the result here must have a norm less than or equal to the norm over here, because this factor here is a positive element with norm less than or equal to 1. But now we notice that this expression here is just the star of this expression here. So actually now using the C-star property, we get that this is just equal to this expression here. But this is just equal to the norm of A squared. And then we can use the fact that the norm is a star isometry, or the norm of the star is the same as the norm of the original object here. So then we get this, and then we get this inequality here. Very nice. So the norm of A star A is greater than or equal to the norm of A squared, which is in turn greater than or equal to the norm of A star times A. So we have proven the C-star property holds. And from all of these calculations, we've shown that the C-star property holds, and thus we have that this quotient algebra is indeed a C-star algebra as claimed. Now, from all this, we can get to maybe the second important theorem, or maybe a slightly more important theorem, because the last theorem we talked about how if we had an ideal of a C-star in a C-star algebra, then we can take the quotient and we get a new C-star algebra being the quotient algebra. What that result really says is that every ideal in C-star algebra is the kernel of this quotient homomorphism, or the quotient map, or rather, it is the kernel of homomorphism of C-star algebras. But there are another sort of dual side to this, and it's the following: that if pi here is the homomorphism of C-star algebras from A to B, then first off, the norm of pi is equal to 1, and the image of A under pi is the C-star subalgebra of B. And moreover, if pi here is injective, then it has to be an isometry. And more generally, if we can say that pi here factors as pi with a dot over times q here, where q is the quotient map of A onto the quotient A quotient kernel of pi, and pi dot is the induced isometric star isomorphism of the quotient onto pi of A. And this is quite a big deal. So let's prove this result in two parts. So we begin by proving that this map phi, or this homomorphism phi, is continuous. And we do it first by looking at self-adjoint elements. So if A is self-adjoint, then by the multiplicativity of pi, we have that the spectrum in B of pi of A has to be a subset of the spectrum of A in the C-star algebra A. And hence, we get that the norm of pi of A, which is equal to the spectral radius of pi of A, is less than or equal to the spectral radius of pi or of A. And of course, we have that the spectral radius of A is just the norm of A. And this is true for every self-adjoint element. So, for general A, we have that the norm of pi of A squared is just equal to this expression here by the C-star property. But this is, of course, less than or equal to this expression here, because A star A is self-adjoint, and the norm of A star A is just equal to the norm of A squared due to the C-star property again. And thus, it follows that the norm of this map phi or pi is less than or equal to 1. And in particular, this implies that pi is actually continuous. And now this in turn implies that the kernel of pi is closed. And this is something that you can prove if you don't believe me. It's not that difficult of a proof. And moreover, pi now, because we have this continuity and then that this kernel is actually a closed and two-sided ideal, that pi, our map pi, factors through this quotient, which we know is actually a C-star algebra now, as pi equal to some pi with a dot over times q, where q is this quotient map that we have. So, by construction, this map pi dot with a dot over is injective. And like going forward, I will just say pi when I have pi dot. So don't get confused over that. And generally, if I say a dot, a, I will mean this a with a dot over. So our map pi is injective. And let us now assume that it's not isometric. Then there must be an element a in this quotient such that the norm of pi of a is strictly less than the norm of a. And as a result, we have some number r, which is the norm of pi of a star a, which has to be less than, strictly less than, that is, the norm of a star a, which we call s here. And note that these are of course positive numbers as well, because otherwise this would make no sense whatsoever. Now let f be a continuous function on the interval from 0 to s, and let us define f in the following way. So f of t is 0 between 0 and r, and f of s equals to 1. So we have f here going something like this, and then it goes up like this. We have r here and s over here. So nothing strange really at all going on. Then, by using continuous functional calculus for self-adjoint elements, we have that 0 is of course equal to f of this guy over here, which is not really strange at all. F of this guy, since the spectrum of... What is going on? The spectrum of this one is of course between 0 and r. We get that f of this is just equal to 0 everywhere. But this has to be equal to pi of f of a star a. And this basically boils down to just pi here being a homomorphism. But this does not really make any sense, does it? Because f doesn't really vanish on this spectrum here, because f of s was equal to 1. And as a result, f of a star a can't be 0. And now since pi is injective here, so this map is injective, and it sends something to 0, then this has to be 0, but it's not 0. And so this is a contradiction, and it follows that this map pi is indeed isometric, and we can't find an element a like this. And from all of this, we conclude that pi of a is closed, and it's therefore a C-star subalgebra V as well. And as a final note, since the norm of this pi with a dot over is equal to 1, and Q is simply a quotient map, it follows that the norm of this map phi, or this map pi, is 1 as well. So, to recap, first off we have that norm closed and two-sided, or maybe I shouldn't even say that, ideals of C-star algebra are by necessity self-adjoint. And thus, the quotient algebra of A by any ideal I is a C-star algebra if A is. And this immediately implies that every ideal is the kernel of a homomorphism. And conversely, any homomorphism that we take, which is phi from A to B of C-star algebras, can be factored over this quotient as pi dot times Q, where Q is the quotient map, and pi here between the quotient algebra and the image is an isometric star isomorphism of C-star algebras. And I think I will end there today. And then maybe next time we'll start talking about representations of C-star algebras or something like that. We'll see when I have the time to make that video. As you may have noticed, this one took a long time for me, and that was because, well, sometimes life gets in the way of making videos. Hope you're having a good time. See you later. I'm signing off. Bye.